Charles Pence is not originally from Louvain, Université Catholique de Louvain, but he moved to Louvain recently. Was it last September? Right?
Yes.
August, September. From the US, obviously. And Charles is there a professor of philosophy of biology in a group that has several philosophers, including in philosophy of physics, my good friend Alexandre Gay, and also they have many interactions with scientists and medical doctors, a little bit on the same kind of model that we have here. And Charles has been doing very, very interesting job on very different topics, one being chance in evolution, and also different interpretations of fitness, including the propensity interpretation of fitness, which is a very big thing in philosophy of biology and theoretical biology. Charles also has, in addition to philosophy of evolution in general, and chance in particular, Charles also has many interests in different issues, including the digital humanities, a topic on which he wrote different things recently, so that was also very interesting for us. He's the author of several papers that you can easily find by just clicking on the link we have on the website. And today, Charles suggested this topic, which I think is extremely interesting for many of us, bringing statistics to evolution, with the title, The Wonderful Form of Cosmic Order. So Charles, thank you very much for having accepted our invitation.
Certainly, thank you. I'm really, really excited to be here. This is a lot of fun. It's a beautiful place, and obviously a very cool, very active group. So I'm very excited to get a chance to talk to you guys. Also, sort of luckily, this project sits at the sort of happy intersection of two book projects that I'm in the middle of wrangling with right now. One on the history of the introduction of notions of chance and statistics into evolutionary theory, broadly from about 1859 with Darwin through something like 1930 or 1940. I haven't written my way to the end of the book yet. We'll see how far it goes when that happens. And another on a shorter volume on the sort of philosophical upshot of some of the work that I mentioned on the foundations of evolutionary theory, the sort of causal and conceptual foundations of evolution. And this is a fun place where actually I can bring the two of them together. So let me give you an idea of what I'm going to do. I'll frame the talk by sort of introducing a historical paradox that I think is very puzzling when we turn to the history of biology and the period around and immediately after the death of Darwin. To do that, we'll be looking at Francis Galton. So where we're headed is for a sort of detailed understanding of natural inheritance, which is taken to be Galton's magnum opus, his major work. We'll get there via some of his early stuff, sort of ways in which Galton was introduced to notions of chance and statistics. In particular, once we get to natural inheritance, we'll talk a little bit about Galton's model, although notably entirely in the absence of any biochemistry, of what particulate inheritance might look like, a bit on his connections between chances and cause, and a bit on at least what Galton thinks he's doing when he talks about natural selection. As we'll see, it's very unsatisfying. Interestingly, sort of this opens out to a research program for a broader group of scholars over the course of the first couple decades of the 20th century and leading into the modern synthesis, the construction of contemporary evolutionary theory. That's the biometrical school, so I'll talk about how Galton gives rise to that. And then close by stepping back a little bit, because I think what makes Galton interesting, I think part of the reason that Galton forms a sort of group of people around himself is that he's put his finger on two really crucial, really important, recurring questions in the philosophy of science, at the very least as regards evolution, and maybe a little bit more speculatively, I want to say, in a theory that we'd have to think of in statistical terms. So I would expect these kinds of worries to come back. So as I said, I want to introduce the talk by framing a sort of very paradoxical combination of facts about the history of biology. So of course, I'm pretty much like morally obligated. Every talk I give has a picture of Darwin in it. It has to show up at some point. This one I like because, in fact, Darwin was not born with a beard. There did exist a Darwin who did this. So this is Darwin in the mid-1850s, just as he's starting to turn his attention to writing down the theory of evolution for the first time. So he publishes The Origin famously in 1859. Massive change throughout the scientific community. All sorts of people become deeply, deeply interested in what he's doing there. One of the people who becomes most interested in it is Darwin's cousin. So this is Francis Galton. He'll be sort of our central figure for the day. Before he reads The Origin, Galton has been sort of a more or less successful geographer. So he's run several expeditions to Africa to map various parts of the African continent, although I'm never quite sure how seriously he was really taking it. Right between, in his autobiography, between two chapters about his geographical expeditions, is a chapter called Hunting and Shooting. So maybe he's not the world's most dedicated scientist at this period. Now, the standard story, or at least the standard story about Galton, then turns to the following thing, that Galton has a massively important impact on the entire first generation of statistically grounded evolutionary theorists. So this is Carl Pearson writing in an obituary for W.F.R. Weldon, about both of whom more in a little while. But Pearson says the next year was to place in Weldon's hands a book, Francis Galton's Natural Inheritance, by which one avenue to the solution of problems in evolution, one quantitative method of attacking organic correlation was opened out to Weldon, and from this book as source spring two of the friendships and the whole of the biometric movement which so changed the course of his life and work, right? Natural inheritance literally changes Weldon's life, right? This is supposed to be a big deal. And by a bunch of people similarly positioned, it's taken to be a sort of genre-defining moment in the history of science in general. So this is in Pearson's biography of Galton, which he later writes. About natural inheritance, he says, no one who studied it on its appearance and had a receptive and sufficiently trained mathematical mind could deny its great suggestiveness or be other than grateful for all the new ideas and possible problems which it provided. The methods of natural inheritance may be antiquated now. As we'll see, Galton's methods are very clunky at this early stage. Statistics is a very young science. But in the history of science, it will be ever memorable as marking a new epoch. Wow, okay. This is pretty high praise. And it's not just contemporary praise. So if any of you know, Ian Hacking's masterful, this is a sort of synthetic historical tale of the development of methods of statistics and chance over human thought. It's really remarkably wide-ranging. Hacking gives Galton sort of real pride of place in this story. Hacking says that Galton is the very first person to use the tools of statistics in what he calls an autonomous way. That is to say, the idea that statistics could explain the way that something happens in the world sort of independently of the underlying description that may or may not give rise to the statistical facts. And hence, Galton is, in a very strong sense, the person who tames chance. He's the first person to do it. Or at least he's a very important player in the story. So much for the sort of first half of the paradox. There's sort of standard narrative part one. Paradox part second is Galton's really bad. When you actually go to read them, he's not very good. These books are not well done. This is from Bernard Norton's dissertation. He's talking about Galton's eugenical work on natural ability. I'll come back to eugenics in a moment as well. But he says the argumentation concerning this concept was, as frequently with Galton, very bad. But the concept was powerful, if vague. Seriously faint praise, right? This is very, very limited, very limited positive valence here. Galton's more or less terrible at constructing philosophical arguments. He has this infuriating habit, which actually I'll give you several examples of switching. He'll be giving you this really interesting theoretical or philosophical argument about some claim, and right at the point where the details start to matter, he just brings in a physical model of the system. It says, so it works like this box with pellets in it. And you're like, wait, no, you hadn't gotten to the good part yet. He's often ambiguous to the point of being internally contradictory. So this is an article by historian of biology Peter Bowler. He's writing about Galton on natural selection. And so even at the time, not just from a contemporary perspective, contemporary textbook author Brooks included a whole chapter on Galton in his textbook and explicitly addressed the ambiguities in his writings by quoting passages that seem both to support and to deny a prominent role for natural selection. Right? So even at the very time, he, at least on natural selection, he's taken to be so confused, it seems that he's simply ambiguous on the question of the role played by natural selection. So this, in essence, is the paradox that sort of animates this piece of the project, right? Why Galton? Why is Galton so taken to be so important? If Galton is really pretty profoundly mediocre, why is he one of the most important figures in the story that we tell ourselves about the introduction of statistics to biology? So a brief aside, one thing that I'm not going to do, and there's another reason for which undoubtedly Galton is very important and very significant, is I'm not going to talk about eugenics. So Galton is now very well known as being one of the central figures in the British eugenics movement at the end of the 19th century. I, to be perfectly honest, don't know whether it is sort of intellectually forthright to avoid talking about eugenics, but I'm going to. As best I read Galton when he talks about many of the points that I'll be really emphasizing here, they're broadly separate from his eugenical concerns. Of course, he wouldn't have been interested in any of this at all in the first place if he weren't motivated by a sort of deep and overriding belief that something's wrong in society and we need to fix it. So this sort of eugenical thinking is very deep in Galton. But that's not going to be my focus here today. If you're interested, the history of eugenics industry is very broad. It's a very wonderful literature. I'd be happy to give anyone pointers. It's a very difficult field, but it's quite rewarding to study. It's a very depressing chapter in human history. So with that, let's get into Galton himself. So Galton's early work. If we want to understand what he does in natural inheritance, what he does in his later sort of magnum opus, we need to understand early Galton. And there's a number of ways to trying to figure out what early Galton is doing. One of them, of course, is via eugenics. The one that I think is most fruitful for the kinds of questions that I'm interested in is to approach Galton via Adolphe Quetelet. So this is Quetelet, astronomer royal of Belgium, now recognized as one of the central figures in the development and use of statistics in the social sciences. Right, so Quetelet is a very early, very important pioneer in this regard. He's also Galton's introduction to statistical reasoning, writ broadly, to in particular the sort of many and multifaceted roles of what we now today would call the normal distribution, a normal curve. And much, I think, of the picture of chance that Galton takes away and carries into his later work actually derives from the work of Quetelet. So I think it's useful for us to unpack this a little bit. The first thing to realize about Quetelet on statistics is that Quetelet is profoundly and deeply weird. He's a very, very odd figure. He develops an approach to mathematizing the social sciences that no one else ever uses ever again. It's completely idiosyncratic. He builds, in particular, his sort of initial approach to the entire idea around this funny concept of l'homme moyen, the average man. It's convenient to deliver this talk in front of a francophone audience. I can just put that up there. The man that I consider here is, in society, the analog of the center of gravity in bodies. He's the mean around which oscillate the members of society. It is, if you will, a fictitious being for whom all things occur in conformity with the mean results obtained for the society. If one looks to establish, in some sense, the basis of a social physics, it's him one must consider, without dwelling upon particular cases or anomalies, without seeking whether some individual may have obtained greater or lesser development in one of his faculties. Now, very often, right, in the life and social sciences, we hear about this worry about physics envy, right? That people are sort of obsessed with making their sciences seem like the physical sciences. Oftentimes, I think that is actually an overblown worry. I think people aren't really doing that, and to the extent that they are, there's not really anything wrong with it. It's very definitely true for Quetelet, right? Quetelet absolutely wants to build a theory of statistical life science that just looks like the behavior of ensembles in physics. And so just like we think about the center of gravity of a physical system, we're going to think about the average man, right? Underneath the statistics is the real thing that the statistics are supposed to describe. And so the real thing for social science is this average person out there that we're supposed to think in some sense is really an object of study. It's a very foreign way of thinking about bringing statistical inference to social sciences from a contemporary perspective. So we're seeing some very extreme abstraction, right? This is already clear from very early on. And at the same time, the other feature of Quetelet that I think is important is Quetelet is very impressed by the extent to which these distributions are sort of static, unmoving. So I think everyone who writes in French has to sound vaguely like an existentialist. It's sort of a requirement. What sad condition of the human race? We can enumerate in advance how many individuals will dirty their hands with the blood of their fellow men, how many will be counterfeiters, poisoners, more or less like we enumerate in advance the births and deaths that must take place. Elsewhere, Quetelet does say, he sort of pays lip service to the idea that, well, with social change and education, we might be able to make society better. But it's very hard to see how he could mean it, given the sort of really static picture of statistical distributions that he seems to have. Now, Galton reads Quetelet and in his own vaguely racist way is extremely impressed by it. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of error. A savage, if he could understand it, would worship it as a god. It reigns with serenity and complete self-effacement amidst the wildest confusion. The huger the mob and the greater the anarchy, the more perfect is its sway, right? So Galton is really, really floored by the potential utility of something like the law of error. In the 1860s, then, he has this idea that he's basically going to be able to solve heredity. So he's brought in this tool from Quetelet, this statistical tool from Quetelet. Darwin, in the meanwhile, has proposed the theory of pangenesis. This is Darwin's hypothesis for the physical underpinnings of inheritance, these hereditary particles that we cast off by all parts of an organism and accumulate in the reproductive organs. And so Galton's pretty sure other biologists will work out the details of pangenesis. He'll work out the details of the statistics of transmission, and everything will be great, right? We will have just solved this problem for all time. There's just one problem, and the problem is discovered by Galton himself. The problem is rabbits. So Darwin's theory of pangenesis has it that these elements of heredity are constantly being cast off by all of your organs. This is how Darwin wants to explain the fact, as he sees it, that characters that we acquire during our lifetime could be inherited to our offspring. So blacksmiths could have children with beefy arms. This only makes sense, right, if throughout the course of our lives, sort of information about our state is sort of being passed into the reproductive system. And so Galton has the realization that blood transfusion, having been just developed and perfected around this time, could actually could provide a legitimate experimental test for Darwin's theory of pangenesis. So he takes a bunch of rabbits and he connects them in a massive transfusion and breeding experiment. He essentially swaps the blood between them. So if he's done that, right, he should also have swapped the migrating hereditary characters that are floating around in the bloodstream. And then he breeds the rabbits after he's done so, and what he discovers is there's no transmission. There's no change in inheritance at all. By doing this, of course, we now understand exactly. This is widely taken, I can say more in the Q&A if people are interested in the fine details, this is widely taken to be fatal to pangenesis. So on the one hand, right, what you have here is, here disappears the biological grounding of what Galton thought his answer to this question would be, right? He thought he had this part solved. He was expecting to vindicate Darwin, right? Darwin is his cousin, and he actually loves pangenesis. He's heartbroken to destroy this theory, as it turns out. Darwin writes in these really sort of pained letters, like, how could you? On the other hand, though, he's tightening up the statistical side of his work at the same time as this. So in a lecture in 1877, he sort of really gets clear on the statistical end of this for the first time. So I think here we really see his debt to Quetelet. He says, the outline of my problem of this evening is that since the characteristics of all plants and animals tend to conform to the law of deviation, let us suppose a typical case in which the conformity shall be exact, and which shall admit of discussion as a mathematical problem, and find what the laws of heredity must then be to enable successive generations to maintain statistical identity. So you can see what he thinks at this point, what he thinks the fundamental problem is, right? Organisms have offspring that aren't like them. Organisms vary. This is one of Darwin's fundamental pieces of data in The Origin of Species. So how could it be, even given that we see basically the same distribution of characters across multiple generations? If you measure the height of a human population over the years, at least this is all the data that Galton has, it looks like it's pretty much the same. So how does this work? Right? So stasis is the problem for Galton. Galton says we should expect variability. Stasis is what's actually interesting. Again, here's this bait and switch thing. To spell this out, he gives you a physical model. So you've probably all seen one of these in a science museum. This is Galton refers to it as the quincunx, after this pattern of five dots. The nails are hammered in. You'll also hear it called a Galton box. And lo and behold, if you've never done this demo, you put a bunch of pellets or shot up in here at the top, and you pull the cork out, and you let them cascade down to the bottom, and every single time they form a beautiful normal curve down there at the bottom of the device. It's like magic. It's a really lovely little thing. Now the reason for this, along sort of Quetelet-type lines, is completely explicable. I'll come back to those other two devices in a second. In addition, Galton writes, to the constant effects of the mean, that is to say you drop them all in at the same spot, and gravity, they all fall down at the same rate, there are a host of petty disturbing influences, represented by the spikes among which the pellets stumbled in all sorts of ways. The theory shows that the commonest case is that where a pellet falls equally often to the right of a spike as to the left of it. It sort of lands in the box directly beneath the funnel. It also shows that the cases are very rare of runs of luck, carrying the pellet much oftener to one side than to the other, winding up in one of the extreme buckets. This is how you get a normal curve. And this is exactly the way that Quetelet said normal curves always appear. If you have a bunch of people trying to measure the same thing and they keep making small mistakes, well, eventually that's going to produce a normal curve. He uses these other two devices to describe some other various features of normal curves. Figure 8, for instance, is his answer for why it is that these curves are constant across generations in spite of variance, in spite of individual variability, I should say. Says, imagine that you stop up the device at the middle and you let the shot run first to point A. You'll get a little normal distribution, right? And then imagine that you remove one of these little stoppers underneath one of the columns and you let the shot cascade down from it. Well, you're going to get another tiny normal curve that's centered around the hole that you opened up. But the interesting thing is, so if we think about, we come down here and we think about where the extreme offspring, if you will, in B came from. So these pellets that wind up here, where were they up here? Well, some of them were out here on the edges of the distribution. But many of them, more of them in fact, were in the middle. Why is that? Well, because there's so much more shot in the center, the odds are better, actually, that, and if you will, to translate into biological terms, that an average parent would have extreme offspring. There'll be more extreme offspring that come from average parents than there will be extreme offspring that come from extreme parents. So that's how we get sort of reproduction of these normal curves over time, in spite of the fact that individuals vary when they give birth to their offspring. If you're worried about the fact that the variance would go up from A to B, then he's got that covered too. That's what this little squeezy is supposed to do. It's a sort of arbitrary hack to make variance go down. You just squish the curve from the sides. Again, these methods are primitive, as Pearson said. So, good as far as it goes. This is several of this collection of boxes is going to give you nice physical analogies for several of the properties that Galton was interested in explaining. But there's still one big problem here, and that's that we have absolutely no idea why this would apply to living organisms. So, as Galton puts it, we know that characteristics of plants and animals conform to the law, but the reason of their doing so is as yet totally unexplained. The essence of the law is that differences should be wholly due to the collective actions of a host of independent, petty influences in various combinations. But the processes of heredity are not petty influences, they're really important ones. So how is it that the hereditary process still manages to give us normal distributions, even though, in many cases, we won't be able to help ourselves to this Quetelet-style explanation of a bunch of little bitty offsetting, independent petty causes. And so this is the task that Galton sets himself in natural inheritance. This is Galton's job, is to sort of give us a solution to this problem. And to do it, what he realizes is, in some way or another, he's going to have to give us a replacement for pangenesis, right? The underlying account disappeared, and it hasn't come back yet. So where did it go? And what can we say about what's going on at the level of sort of individual inheritance without having any of the biological data that we eventually would have, for instance, after the development of genetics? So he sets about this from the very beginning of the book. This is page 9, right? We know that organisms more or less inherit traits as sort of packages, right? Morphological traits tend to come more or less, with some exceptions like height, although we'll talk about that, more or less as sort of discrete units from your various parents, and, which will also be very important for Galton shortly, your more remote ancestors. So Darwin was at least right that the system of heredity has to look something like particles, each of which are responsible for the development of particular characters being passed on to offspring. So what we need is some kind of a system whereby, while the embryo is developing, there's a bunch of these particles that are in competition, right? The particle is more or less qualified for each new post. Wait as it were in competition to obtain it. Also, the particle that succeeds must owe its success partly to accident of position. This is how Darwin talked about the particles in pangenesis. And partly to being better qualified than any equally well-placed competitor to gain a enlargement. Two things about this. One, he loves these political metaphors. They're everywhere in his books. At one point he talks about, many points actually, he talks about inheritance like parliamentary governments. But also, to the extent that he alludes to a sort of individual particle selection here, it's very not clear what he means. It's a very sort of tantalizing Galton fragment. Furthermore, as I mentioned briefly, these characters don't only arise from the parents. So Galton is really seized by the phenomenon that every once in a while you'll see in an offspring a character that hasn't perhaps been seen for multiple generations in the history of the lineage. Darwin was shocked by the same thing. When Darwin writes about pigeons, one of the things that he says that's really good evidence that all pigeons are descended from the same stock is that no matter how fancy, you get these fancy pigeon breeds that these strange English gentlemen are breeding in their backyards. Every once in a while, one of these very derived, very fancy pigeons produces an offspring that looks like a dirty street pigeon. Absolutely exactly. That's weird, right? If we sort of stop for a second and think about how we might be thinking about inheritance in 1889, That's a bizarre phenomenon. It's going to be difficult to make sense of that phenomenon in context. And so Galton's really struck by it. And so he goes out of his way to emphasize the fact that children inherit partly from their parents and partly from their more distant ancestry. There's a bit more of the fun technical stuff here. He also says that this is the reason that, at least according to his measurements at the time, the regression coefficient of offspring among parents is going to be about 2/3. Why? We would expect it to be somewhere between 0, that is to say, all the characters come from distant ancestors who just look like the population at large, and 1, all the characters come directly from the parents. So it turns out it's about 2/3. Galton says that we should have expected this. This is exactly what the statistical relationship should look like. Now we can easily solve this problem, though, if we think a little bit about what these particles of inheritance are actually doing. Some particles, he says, are active, that is to say they're displayed in the offspring. He calls them patent characters, and some are suppressed. They're latent characters that are present in an individual, passed on to future generations, but not currently being, as we would say, phenotypically expressed. So what Galton does in the first part of the book, then, is really to do his best to theorize in a near-complete data vacuum, except for a little bit of this stuff about statistical distributions, what these inheritance particles, how they would have to behave, what they would have to look like, in order to produce, to sort of save the kinds of phenomena that Galton is particularly interested in. So, that's the interesting thing number 1, Galton trying to reconstruct this picture of particulate inheritance. Interesting thing number 2, we still haven't explained how it is that these statistical distributions arise from this particulate inheritance model. So how is it it occurs? By and large, Galton gives us a pretty unusually simple explanation of this fact. He says, look, it's just approximation, more or less. At the end of this first chapter, he says its intention has been to show the large part that's always played by chance in the course of hereditary transmission, and to establish the importance of an intelligent use of the laws of chance and of the statistical methods that are based upon them in expressing the conditions under which heredity acts. Right? As an aside, this is the basis of, I actually really think Hacking is wrong about pinning Galton as the first person to use statistics in this autonomous explanatory way. He talks very clearly about just using these statistical laws as a way to approximate, as a way to understand the conditions of heredity, to sort of back up from the messy data that we might get about particulate inheritance. And he says we should have expected this the whole time. So a parade of great accuracy is foolish, because precision is unattainable in biological and social statistics, the results being never strictly constant. What do we need? We need what statistics gives us, which is no more than a fairly just and comprehensive method of expressing the way in which each measurable quality is distributed among the members of any group. Right? All we're really doing is thinking about how these characters are distributed among populations. One might appeal, for instance, to practical utility for eugenics purposes right here. Right? We just care about how these characters find themselves laid out in a population so that we can make interventions on it, if necessary. Now, if you're wondering about how on this kind of view we should understand evolution, this is a very good question. So this is the last important thing from natural inheritance. How are these populations supposed to evolve? And as I mentioned with that quote from Bowler in the introduction, Galton is really unsatisfying on this point. He considers natural selection broadly in 2 ways. One, he introduces a physical model, again, about which I could say more in the Q&A. In essence, what he does with the physical model, though, is he defends what we would now call a saltationist picture of evolution, evolution that moves by jumps rather than gradually. So characters sort of appear wholesale as a result of significant single variations. When he talks about evolution in statistical terms, it's quite bizarre. He only considers the case in which the mean at which the population now finds itself is also the fitness optimum, the selective optimum, the thing toward which natural selection is driving. In contemporary terms, he only thinks about stabilizing selection. Now, again, I think this is very Quetelet-inspired, if you will, right? He even gives us an argument for why this would be a good way to think about natural selection. He's deployed this whole analogy with warships now. Again, he loves these weird analogies. He's built this whole analogy with kinds of warships, but he says evolution might produce an altogether new type of vessel that shall be more efficient than the old one, but when a particular type of vessel has become adapted to its functions through long experience, it's not possible to produce a mere variety of its type that shall have increased efficiency in some one particular without the rest. It's just so it is with animals. I love that. Like, that's the argument that this applies to evolution. So it is with animals. But you get the idea, right? Organisms are so intricately internally connected and related that you can't just grab one parameter and vary it. So what we should actually expect is basically every organism is basically maximally adapted all of the time. It's a radical adaptationist view, a perfectionist view, if you will. Darwin sounds like this at points. So this is really a very static picture, right? This is a very, when he uses statistics to think about evolution, he's using them in much the same way that Quetelet was. He's impressed by the fact that these distributions look the same over time. So much for natural inheritance. What happens next? So if this is where Galton leaves us in 1889, what happens next? The first thing to say is Galton pretty much stops. Here's a nice agent, Galton. Galton pretty much stops contributing, with one interesting exception. I'm hiding the ball, but that's in the next chapter of the book. Pretty much stops contributing to the analysis of heredity in this sort of broad theoretical way. He basically becomes a public proselytizer for eugenics. He spends the last decade of his life arguing for broad public eugenics programs. But as I noted at the beginning of the talk, there are others who take up the mantle. So this is Galton on the right. On the left is Carl Pearson. So if you know of many of the things in statistics that have the name Pearson attached to them, they're named for his son, Egon Pearson. But Carl himself is also a real innovator in really the pure technical mathematical branches of statistics at first in his career. So if my memory doesn't fail me, he develops the chi-square test for goodness and fit, for example. But then later in his career, or toward the middle of his career, he meets this man, W.F.R. Weldon, who is a practicing marine invertebrate biologist, who takes Pearson's interest in statistics and bends it toward the biological realm. The two of them sort of together go off and found what will go on to be the first major school of statistical evolutionary theorizing. So what do they get from Galton? That's, again, to sort of keep zooming out steadily. What this sort of bizarre inheritance that Galton has left us with? What are they seeing as so pivotal to draw out of Galton's work? Perhaps unsurprisingly, I'm going to say that it's exactly the things that I just gestured at in my presentation of natural inheritance. Surprise? First and foremost, Galton, I think, is the first theorist of evolution after Darwin to really draw on this connection between heredity and the deep past, deep ancestry. This really be worried about these phenomena of significant reversions to deep ancestral characters. And by extension, he's the first person to realize that even in the absence of biochemical data, we could use a theory of particulate inheritance, however qualitative and without sort of serious empirical backing, to really understand how this connection might work. This could be a way that we could really try to get some leverage on answering these kinds of questions. And this is a challenge that we've taken up by the biometrical school. They never really quite figure out how to deal with it. Pearson stops doing evolution for various reasons before he finishes an answer to the question, and Weldon dies of pneumonia. Weldon leaves a pretty suggestive answer to this question in an unpublished manuscript that I'm going to be working on a scholarly edition of here pretty soon with Greg Raddick, so watch this space. But they keep being worried about this question, and to the very end of the biometrical school, they recognize this as a class of phenomena that they really have to save. The other thing, of course, is Galton's picture of evolution is essentially static, right? We have these distributions, they basically pass on uninterrupted into the future. That's the interesting feature. Statistics can help us understand why that happens. And that was fine for Galton, but within 5 or 10 years after Galton stops publishing, what becomes the really, really important fact about evolution is evolutionary change. The debate becomes about variation and selection, how we should think about populations changing over time. And so these future figures, they can't just say, stasis is the important thing, don't worry about the dynamics. That stops becoming a tenable kind of position. So this Galtonian idea that we're basically using statistics to explain stasis, to compare distributions to one another, to show that they haven't changed at all, that's going to leave a wide open intellectual research program to Galton's intellectual ancestors. How can we understand a particulate theory of heredity that makes room for the influence of deep ancestry, and how can we then use that to construct evolutionary dynamics that change over time? So now let me close by being a touch more speculative. So I think that this is actually due to Galton's having seized upon two really deep, really interesting philosophical questions about how we might interpret theories like evolution. Again, I'm not really qualified to make this connection, but I think we would also see them arise in the context of other statistical theories. I would expect them to show up in the social sciences. I would expect them to show up in statistical physics, for instance. So first, our discussion of particulate inheritance really drives us to think about some old-fashioned philosophical question, the relationship between theory and world. You know, we have these statistical theories. The biological theory that tells us that what's interesting are these various kinds of statistical distributions and trends. And then we have a bunch of things down there in the muddy, messy biological universe that we like to understand how they actually work, things like little bitty inheritance particles. What's the connection between those two things? And that's a very, very old philosophical problem, right? But it's made very acute when these kinds of trends, when the kinds of theories that we're looking at are probabilistic or statistical, right? It's much easier to tell a story like this in a Newtonian world, where you have a bunch of little particles that run into each other. The theory tells us not only about how the aggregates work, but also about how the individual little pieces work. We can't use that kind of explanation, or at least not obviously, in a context like this, not without a lot of work. And that's a very serious, very deep, but very long-standing philosophical question here. And Galton had used this sort of vague hand-waving and approximation to try to answer this, but even the people right after him, Pearson and Weldon, don't see this as a very satisfying answer to this kind of question. So it becomes immediately a really pressing thing for them to try to resolve. And second, how do we express evolutionary dynamics in statistical terms? This is really interesting because I think here we owe it to ourselves to try to put ourselves in the place of these historical actors. So for us now, it's very easy for us to think about how a statistical theory can adequately and readily explain the dynamics of a system. We have lots of these kinds of statistical theories now, right? This is a very standard way to build a scientific theory. We're used to it. It's familiar. But I think it's important to say that it was by no means clear in the 1880s that we would be able to do this, right? That statistics would be useful for doing anything but talking about these sort of static characterization of variation out there in the world, right? This is a really unusual thing to decide to do if it's not something that you're sort of already on board with, if it's not something you've already thought of. So that, I think, is sort of way to resolve this historical paradox that I opened the talk with, right? Galton is indeed not that great of a constructor of argument. He's exceedingly vague, but what he manages to do, and the reason that his work continues to be picked up by people in his immediate aftermath, is precisely because he's hit on these two really interesting philosophical questions in the analysis of statistical theories, and they're problems that stay with us today as contemporary philosophers of science. So with that, thank you very much, and I'd be happy to take any questions.
Thank you very much.
And don't mind me if I'm scribbling furiously. I always try to take notes during a Q&A because I want to take these home. This chapter is not quite finished yet, so I'm happy to do that.
So you can even influence a chapter.
Yes,
That's good.
yes. You'll all be in the acknowledgements.
Questions? Remarks? Mate?
Has Galton ever thought with as much dedication of applying his ideas to other phenomena than natural inheritance?
Not to my knowledge in his work, no. Except to the extent, except unless you think that eugenics counts as a sufficiently different set of phenomena, which I'm not sure that you should. I think I would see them as roughly continuous. One of the things that is a bit surprising about this period is, and this at least holds for everything that I'm familiar with from Galton and from Pearson and Weldon who follow him, you might expect, for instance, fertile cross-pollination with early statistical physics, which is right in the middle of being developed. I mean, it's a really important, it's a crucial time to the 1880s in statistical mechanics. It's huge, right? As far as I can tell, there's just basically none of that. They're not reading these guys, which is very odd, but that's as far as I can parse the historical record, that's what it's telling me.
But maybe at the same time it suggests that it's not that weird that the statistics are not necessarily very good and very developed, because even in physics it's not that developed in the 1870s, for example.
Yeah, no, it's important to emphasize. I mean, when Galton is writing, and the first couple works, say the first paper by Weldon to come out when he starts doing biometry, I mean, we have no goodness of fitnists. So they're drawing normal curves out of a book and then drawing their data and going, that looks pretty good. You know, they're doing these very crude kind of absolute curve difference measurements. Yeah, the science, the mathematics itself are just still really crude. And so you're sort of seeing, it's one reason I think this period is so interesting, is you're sort of watching the infancy of this sort of mode of thought that now, again, as I say, now seems really second nature to us.
Hi, thank you. That was great. My questions, I have failed to understand the place of these people, Galton and Pearson and Weldon, in the community of people working on the theory of evolution in this time. I'm talking both about the United Kingdom and, of course, France, Germany on that side. If you could say a few words.
Yeah, good. That's a fantastic question. So yes, in particular, it's a fantastic question because Galton has a kind of peculiar place in this community. So Galton himself, as you may know, after Galton, there becomes a really, really venomous debate that emerges over the status and role of variation in evolution, and in particular, in 1900, Mendel's work is rediscovered. And so the correct way of interpreting Mendelian genetics gets sort of thrown into the fire that had already been raging, and everything goes crazy. There's a very serious sort of open war in biology. Galton is interesting because Galton sort of hovers above the fray. Everyone in these debates seems to think that Galton is on their side. He's sort of the grandpa of British evolutionary science in this period. So everyone appeals to Galton for help whenever they get attacked by someone. They'll be like, Galton, help! This other guy said mean things about me. So Galton hovers above this fray, but then the people who really take and run with Galton's idea, Pearson and Weldon, become one of the two parties to this battle, right? They become the sort of pro-mathematical, pro-statistical wing of the British biological establishment. And the classic story that we tell, although it's too quick and in several important ways wrong, it's actually the main thing that I'm trying to display to argue for in this book. The classic thing that we say is that it was them on one side, and it was sort of variationist Mendelians on the other side, morphologically driven variationist Mendelians on the other side, and the Mendelians win. So Weldon dies, Pearson quits studying evolution, Mendel carries the field, until people like R.A. Fisher and Sewell Wright really bring the two back together in the 30s. I think that's too simple, but that at least is kind of the broad structure of what the battlefield looks like, and that's not an inapt metaphor for this period in British biology. The connections to France and Germany, for example, are really interesting. I don't know enough about them yet, and I want to know more. I should make sure to flag that that's a really good question, and it's one that's almost unstudied.
Could you say a little bit more about the potential influence of Galton on Fisher and Wright, for example? Because
Good. So, in large part, telling this story in really good detail is actually the project of this historical book that I'm in the middle of. That is to say, what we often say is that, so Galton's methods are too crude, but they inspire people like Pearson and Weldon to produce more refined methodology that sits dormant for a while, is probably read a little bit by people, is read a fair bit by people like Wright and Fisher. But really, Wright and Fisher sort of reinvent the wheel because they're working in such a different context, Mendelian genetics having been taken up so thoroughly by the field at that point. If I can seriously speculate, because I have not grounded what I'm about to tell you in the kind of historical work that I need to do to really be able to say it out loud and on video. I think that story is too quick. I think a more detailed and careful story will show, I hope, that there are more robust lines of transmission, that this is much less sort of an independent reinvention of the synthesis in the 30s and 40s, that there really is some deep historical context at work here. That's the story that I want to tell. And I have some very preliminary ideas that seem to indicate that it's correct. But there's a lot of work between here and there.
Yes. Another question is, what was Galton supposed to be, taken to be as a scientist? Was he, you said that he was not considered to be a geographer, I suppose. Was he considered as a mathematician, as a philosopher, as a biologist, as a what exactly? And did it evolve over the years?
Yeah, so once he sort of turns his focus to eugenics and evolution, so after he really turns over in the 1860s to start working on this kind of thing pretty much full time, he is broadly seen as a member of the biological community, to the extent that, the word biologist is a bit of an anachronism. It's difficult in the period, but he is considered as a member of that group of researchers. Okay. That's his main focus. With the caveat that the position of eugenics between the biological and the medical sciences makes for a difficult problem of categorization here. It's a biomedico-social enterprise, biomedico-socio-political enterprise. And so trying to capture that side of his work is a bit more challenging. So there is a sense in which he's engaged in very serious, for instance, political activism in the last decade of his life as well, and would have been interpreted, I think, by many of his colleagues in that light as well later in his career. So yeah, a difficult question, but this stuff that I'm pointing to is seen to be just sort of part and parcel of the British response to Darwin.
one question: do you see echoes of the way Galton sees things or describes things, or the way he uses statistics, for example, in today's biology, or do you think it's completely out of today's biology? And
That's a great question. My initial impulse is to say that I don't see echoes of it. And excuse me. That in and of itself is an interesting observation, right? One can say it's perhaps not surprising. The way to put it might be this: it's perhaps not surprising that Quetelet's approach dies. So, to make Quetelet's approach make a little bit more sense, right? One thing that you could say is Quetelet is an astronomer, right? He is the Astronomer Royal of Belgium. So he's seeing statistics as coming out of the tradition of the astronomical law of error. And it's the astronomical law of error, right? There is a real position of the star. It's underneath all those observations. There's a real thing out there. And so the goal is to see how all these little ways in which we make mistakes can let us get to the real thing. And essentially, Quetelet does the same thing to people, right? Here we have this giant, messy population, but there's a real thing. It's this ideal person that would be underneath all of the messy data. It's not surprising that view dies, right? That's just so very obviously inspired by these narrow physical science kind of concerns that that's not a shock. The death of the Galtonian view presents a more interesting question. If my reconstruction is right, why did that go away? And in part, I think the answer is, as I mentioned, that when the focus becomes more on evolutionary change and evolutionary dynamics, it sort of stops being a legitimate reply to say, oh, well, statistics are about stasis. Well, then statistics aren't very important. That would have been the obvious conclusion, right? By the 1890s or 1900s, it would have been, oh, if they're just describing constancy, nobody cares about constancy. Dynamics is where it's at now. So that would be one response. But I'd like to think more about whether there's a sort of deeper and more interesting response, or some sort of theoretical, philosophical reason, right, that this kind of view doesn't make sense, or if it really is purely sort of sociological. I mean, I know that it's been helpful to me just insofar as it's so foreign. To try to get my head around what it would be that Galton would be thinking is a real challenge. I may have done it very badly. We'll find out. See what other Galton scholars think. But it's a really interesting, it's a very bizarre picture.
So maybe concerning the Galton box diagrams, a couple of them that you showed, kind of what are the implications of that, of how he viewed chance in general, and relativistic interpretations mainly about end states, explaining end states of distributions, right?
Good.
So probably I would be curious to hear more on your views on how to interpret those kind of diagrams and interpretations.
I guess what I would say is, there's a paper there that I want to write if it hasn't already been written, because Galton's deployment of these physical models is really interesting. So he clearly thinks that, I guess the way to put this might be, he clearly thinks that he's not doing anything argumentatively objectionable when he sets up an argument in a completely theoretical vein and then says, look at this Galton box. He thinks that's fine, clearly. So that has to imply some really interesting things about what he thinks the argumentative nature or the conceptual role of these physical models would actually be. Like, how would we really understand what is it that they're providing to an argument? What kind of evidence are they? Are we making inferences from them? What I will say is, I think that any such paper is going to be very heavily rationally reconstructive. I don't think Galton himself is going to give us nearly enough clarity to really answer that kind of a sort of, I think, a supremely interesting philosophical question. So I would have to go away and lock myself up for 6 months and really try to do that rational reconstructive work and look at the models literature and try to think about which ones of these might be consistent with what Galton says. But I don't think we're going to be able to extract a very clear answer to it from his own work, unfortunately. But it's a really cool, it's literally a to-do item on my phone in my list of future papers to write, is Galton on physical models.
No other questions? Comments? Okay, then thank you very much for this
Thank you.
excellent talk. Thank you, Charles.
Appreciate it. Thanks.